Hello, Physics 12 students. I am recording this video because I asked you guys to watch this video here from the University of Pennsylvania about Lenz's law, and so what I'm doing today is I'm going to explain some of the stuff in this video. So one of the first things that this professor does in this video is he talks about this situation here where he's dropping the loop through the magnetic field and it slows down. So let me go ahead and explain why this is working. So here we have the vertical dropper, and instead of drawing a circle, I'm going to draw the loop as a square. So this square is falling down, right? It's actually accelerating down, but the velocity is down. Now in the middle of this around this section here, there's the magnetic field, and this magnetic field, it doesn't matter which direction it's going, but we could say it's going in this direction. And so as the loop gets to that point, so if I draw it again, you gotta excuse my, I'm not doing this with rulers and whatnot. So when it gets to here, okay, now we have a portion of this thing inside the magnetic field. So let's say if it's going through like this, then now there is a change in the magnetic field lines that are going through the loop, and they're actually going through the loop, but they're increasing. So what that means is that the Lenz's law states that when you have an increasing magnetic flux through a loop, you will have an opposing magnetic field that is created through an induced current. So therefore, remember, which way are these magnetic field lines through this loop? So they're to the right. Now, I'm not sure if I'm pointing in the right direction. If this video is going to work, we'll have to see after I'm done it. But when I look at my screen, this is the way they're going. So therefore, as we're getting more and more magnetic field lines getting through the loop, as the loop falls, the opposing direction is going to be the other way. So that means the field that the loop generates is going to be in the opposite direction. Therefore, if we take our right hand and grab the loop, now of course it's difficult to see which direction this is because as I've drawn it here, the magnetic field lines are going in. So assume the magnetic field lines are going into the screen because I'm drawing X's there. So therefore, you take your fingers, put the magnetic field lines in the middle going out, and grab the loop with your right hand. That means that the current is like this. Okay? So that's the direction of the current that is induced in the loop. Now, if that's true, that means there's also the current's going to be like this and like this, right? Now, if we analyze this, let's first analyze this bottom portion, not the top, down here, okay? Because this part's not in the magnetic field yet, but this part is. So, if now you have this current going in this direction, right? So which direction is the force going to be on this segment of the loop? Well, if you use your right hand again, put your directions not in the direction of the induced magnetic field, but of the original strong magnetic field of the giant magnet, pointing in, and then you gotta twist your hand around, and now it's pushing up. See? So therefore there's a force on this section of the wire that is up. Okay? So now let's try this again. And now, okay, so let's say the bottom is here and the top is here. Now let's say the loop is down here. And so now in this situation, the magnetic field lines are still going like this. But in this situation, okay, which direction is the current here? Well, now we have less and less magnetic field lines through, because remember, the velocity for this guy is this way now, because it's still going down. So it's not that we have increasing magnetic flux through the loop, we have decreasing magnetic flux through the loop. Therefore, the induced magnetic field will try to oppose this change, which means that it's going to go in the same direction as the original magnetic field, because it's trying to keep it the way it was. And therefore, the induced magnetic field would be in this direction. So this was the induced B field. This is the induced B field. Therefore, what direction is the current? Take your right hand, put your fingers through the loop, right? And grab the wire. And if you'll notice, now my thumb is going down. So that means this is on the right hand side. Oops. And so that's going to be the direction of the current in this case. Now let's see, okay, so it goes like this, and like this. Yeah. So now, which direction is the force on this portion of the wire as it's leaving the magnetic field? So the magnetic field was in this area here, right? So, and then here it was like here. So in this case, it's the same thing again. Take your right hand, put your fingers in the direction of the B field, which is into the screen, thumb in the direction of the current, and push. And so as you can see again, the push is up. And that's the direction of the force. So what this says to us is, as the ring is entering the magnetic field, it's getting pushed up. As it's leaving the magnetic field, it's getting pushed up. In the first case, it's being pushed up from the bottom of the loop, and in the second case, it's being pushed up from the top of the loop. But in both cases, this force is opposing the direction of gravity. And that's why the loop slows down as it's traveling through the magnetic field. Okay? So, this is a super cool experiment, and it's really awesome to be able to explain it in detail like this. So, let's go to the next one. The next video, or demonstration, I should say, that he did was, if we go back to the video here, the next one he did was the one with the he was dropping the magnet through the copper pipe. So let's try and explain this one here. And so the way that we did this is we have the copper pipe, okay, and so here is the magnet. And so the magnet is falling down. So, I mean, at this point, it doesn't really matter which side of the magnet is north or south, but I can just say this is north and this is south. But it wouldn't matter. If we flipped it around, it wouldn't matter. So now the question is, why does it slow down? So the reason for this is because if you think of this pipe as segments of copper looping, okay, because it's a cylinder, it's a cylindrical pipe, you can have currents going in circles through this cylinder as the magnet is descending. So let's assume it gets to this circle first, and we can also put a circle. So these circles basically represent slices of this copper cylindrical pipe. So therefore, in this section, it's moving away from this circle, and it's moving towards this copper circle. What that means now is that there's going to be induced currents in each of these segments of the pipe. So we just have to figure out what direction they are. Now remember, in this case, we drew the magnet's north end on the bottom. That means there is magnetic field lines going this way, right? And in reality, the magnetic field lines are going to, go into the south and out of the north. That means here we've got magnetic field lines going in, right? And so the induced magnetic field of the loop is going to try and oppose this change of increasing magnetic flux through this loop. That opposition is going to create an induced magnetic field that points up. So that is going to create a current. Let's see what direction it is, although at this point that's not important, because what we need to understand is that this B field now is going to fight. What's going to happen is you're going to have north going against north. And so since you have two north, you can consider this a smaller magnetic field, this north is going to fight that north, and they're going to repel. And that's going to slow the magnet down. However, just for completeness, let's see what direction the current is. So take your right hand, put your fingers in through the middle of the loop, and grab the wire closest to us. And so you'll see that the current is like this. Okay? So that's on the bottom, below the magnet. Now above the magnet, again, you have magnetic field lines going in from above. So this perspective, when I draw these X's, it's always looking at these circles from above. Okay? Because the magnetic field lines are going down here, and they're going down here as well below the magnet. Therefore, but see, here's the difference. Okay? The difference is in the circle below the magnetic field is getting stronger. So remember, only a change in flux, magnetic flux, is going to have an induced current and therefore an induced magnetic field. Not a constant magnetic field. It's only a changing magnetic field. So for the loop above, as the magnet is moving away, it is creating a change, but the change is that it's becoming less and less. Okay? And so therefore, the magnetic field here is going to be, it's going to try and keep it as it was, which means that in this case, the magnetic field lines, I'll draw it again, the field lines due to the big magnet are down, but it's becoming less and less. Therefore, the magnetic field here is going to want to keep it as it was. Which was strong. So I'm just trying. I got to get this straight in my head. So this loop is receiving a decreasing magnetic field down. So that change means that the magnetic field is going to be wanting to kept as it was, which means that it's going to be wanting to go down. The induced magnetic field is going to go down as well. So that's the induced magnetic field. Now, that means that, therefore, this thing is going to be a north pointing down and a south pointing up. Yeah, got it right. So not pointing up, but if you think of this induced magnetic field, you can think of the induced field as, but it is pointing down because it's trying to keep this thing as it was. But because the magnetic field is pointing in this direction, now the north end is below it and the south end is above it. Well, let's take a look at the magnetic field of the magnet itself. Well, that is like this. Okay? That means the south end is up here and the north end is down here. But this thing, the south end is up here and the north end is down here. So here's one and here's the other. That means you've got the north and the south interacting, which means it's going to be attractive. Which means this induced, so like if I actually drew this thing, which way is it going to go? The induced B field is down. So if we put our fingers down through the middle and grab the wire, the current on the top loop above the magnet is going to go like this, which is the opposite direction. However, what you have to understand now is that since this is acting as if it's a north magnet above this magnet and the south end of the real magnet is at the top, there's going to be attraction between these two ends, and so therefore the magnet's going to be pulled up. So from the bottom, so at the top it's north-south, which is attraction at the top end, and at the oops, sorry, I guess you can't see me see what I'm drawing there because of my face. Let me try that again. So at the top, here at the top, you've got NS, so the induced magnetic field, and then the actual magnetic field of the magnets. That's going to cause attraction. Okay, but at the bottom, you've got north and a north, like that, and so that they're going to repel. Which means, if I draw it on the magnet itself, the magnet's going to have a force like that and like that. So this is the attraction force and this is the repulsion force, but both forces are going to push the magnet up. effectively working against gravity and slowing it down as it falls through the pipe. Hope that was a little drawn out of an explanation, but I still think it's accurate. So that was the explanation for the loop. Sorry, not the loop, the pipe. Now, if we go to the last one, let's kind of move this up. And this last one was pretty cool. He actually does a demonstration of a spinning disc. There it is, the spinning disc on the magnet. And so if we take a look at how that works, this one's actually a little bit interesting, because what's going on here is that really it's not so important that it's spinning. It's the fact that you have a moving conductor underneath the magnetic field of the magnet. So, you know, I think they refer to this as like could be used for magnetic levitation for a train. So let me draw. This strip basically represents a part of the rotating disc. Okay, so this is a conductor, and this conductor is moving in this direction as the velocity. Now, obviously we recognize, so that on the big picture of this thing, you know, this strip would be here. So it's moving like this as this thing is spinning around in that direction. This portion, right, is moving like that. So we're only going to focus on this area. Now, we have the magnet above, okay, and there are magnetic field lines going, let's say, down here. We don't know for sure, but it doesn't matter because we could do it the other way. So we'll say this is the north and this is the south on top. Now, even though this strip of conductor is solid, there's going to be currents that are created, loop currents that are going to be created here and here, just like the but you see, the thing about these loop currents is that don't think of these loop currents as in this plane. Okay, they're in this plane. So in other words, they're flat on the surface. Okay, it's not, this distance is not the thickness of the conductor, it's the surface of the conductor, the spinning disk. So now, as this portion comes underneath the magnetic field, now you have magnetic field lines going into the loop. Now, I know what you're thinking. You're saying, well, Mr. Ark, this really isn't a loop here. But you see, you can have loops created in that disk. There's nothing preventing loop currents from forming in that solid conductor, and they do. They're called eddy currents. So, as this loop starts to enter the region where we have magnetic field, you'll have more and more magnetic field lines created going down. Take your red hand, put it down through the loop. Oh, now wait, before you do that, sorry. I skipped too quickly. Because those magnetic field lines are going down, and we didn't have any to begin with, there's going to be an opposition induced magnetic field that fights that change. And so now you take your hand, put it up through the middle, grab the loop, and you can tell that the induced current is like that. Okay? So now this is going to repel. That induced magnetic field is going to repel the magnetic field of the magnet. And so that repulsion, now usually, I gotta say, right? Which way is this thing spinning? This thing is usually attached on this side, okay? With like some kind of a string or a rope, or maybe even like a piece of metal. I think there was in this situation, okay? But see, the back end, okay, so remember which way the magnet is going is that the disc is spinning this way, okay? And here is the magnet, okay? So, and it's attached. Now, I'm not sure if this is the opposite orientation to the picture. It might be, you know, the drawing in the video. But nonetheless, this is my example. So now, here on the portion, oh no, I messed it up. Sorry guys. I actually initially drew it as if it was going this way. Uh-oh, I gotta start again. I got this wrong because I said as it's going this way. So you know what? We're gonna have to switch this around, and because as it's moving in, the magnetic field is down, and so the induced is up. Yeah. So my bad on this one. So the velocity, I made it in the wrong direction. So the velocity vector is going to have to go like this. So this portion, I'm not going to change this is correct now. I just had to change the direction of the velocity. This portion here is going to enter first. Everything's the same. I just got the direction of the velocity wrong. So let's say the disk is turning this way. Okay? So the disk from above, the disk is turning counterclockwise. So now this portion here is going to be leaving, and still the magnetic field is going to be down, but it's going to be decreasing, so the induced is going to want to stay as it was, which is down. And so now this portion is going to be attracting. So this is going to be the down and down. So these guys are going to attract. So we're going to have attraction here, and we're going to have repulsion here. Okay? So in any case, the part that has attraction is going to have the attachment. Okay, so I shouldn't have erased that, because the attraction part needs the attachment to negate the force of attraction that it feels with the moving conductor, whereas the other side is going to experience repulsion. One thing you got to understand about this situation is that it's not going to work unless the disk is spinning fast enough. Why? Because the faster it spins, the faster the magnetic field is going to change around these edge areas. And it's that rate of change which creates the attraction or repulsion, the induced magnetic fields. So I hope that gives you a somewhat better understanding of the video, and I'll link the video, the original video, the lenses law demonstration by the Penn State University. I'll link it at the top so that there'll be and also in the description. Okay, thanks for watching, guys. See ya.